Okay, so in this video, I'm going to talk specifically about space translations. And we're going to find that in systems that have a spatial translational symmetry, the total linear momentum is conserved. So let's find, or let's just look at a system that's like that. So let's say we have two particles, particle 1 and particle 2, just for example. And particle 1 has a mass m1, and particle 2 has a mass m2. And particle 1 has coordinates x1, y1, and z1, and particle 2 has coordinates x2, y2, and z2. Now, the kinetic energy of these combined particles are 1/2 m1 times x1 dot squared plus y1 dot squared plus z1 dot squared plus 1/2 m2 x2 dot squared plus y2 dot squared plus z2 dot squared. Now, we could also have some potential energy between these particles, right? Which we'll call V. And in basically the real life examples we'd be interested in studying right now, V, right, would only depend on the distance between our two particles, right? Like, for example, in gravity or with the Coulomb force or something like that. It only depends on the distance between the two particles. So we're not going to say exactly what V is, but we're going to say that it's only a function of the distance between the two particles. And what's that? Well, it's x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. All of that square rooted. Okay, now our Lagrangian is just the kinetic energy minus the potential energy. So our Lagrangian L is equal to the kinetic energy minus the potential energy. Okay, now let's say we wanted to take our whole system, right? Take our whole system and move it around somewhere else in space, right? This would be the same as adding, use a different color now, a constant vector A to the position of both of our particles, right? And A has components, let's say AX, AY, and AZ. All right, so x1 prime, and x1 prime is just our coordinate x after you translated it, is equal to x1 plus a sub x. And then y1 prime is equal to y1 plus a sub y, and then z1 prime is equal to z1 plus a sub z. Now, we do the exact same thing for x2 prime and all the other in y2 prime and z2 prime. So x2 prime is equal to x2 plus a sub x. y2 prime is equal to y2 plus a sub y. And z2 prime is equal to z2 plus a sub z. All right, now the next thing we want to do is we want to show that L equals L prime. Now, L is our Lagrangian when we use our regular coordinates, x1, y1, z1, x2, y2, and z2. And L prime is when we instead use our primed coordinates, x1 prime, y1 prime, z1 prime, x2 prime, y2 prime, z2 prime. And if if L equals L prime, then as we've discussed, we have a spatial translational symmetry. All right. So, just get rid of that. All right. So this is pretty easy to see. This is because, as you could see, for example, x1 prime dot is equal to x1 dot. And that's just because a sub x is a constant vector. It's not changing in time, whereas x1 and x1 prime are changing in time. But because a sub x and also a sub y and a sub z aren't changing in time, then we could say this for anything. So, y sub 1 prime dot is equal to y sub 1 dot, and so on. So this whole first half of our Lagrangian, the kinetic energy term, this doesn't change once we change our coordinates to our primed coordinates. So the kinetic energy doesn't change. Now, does the potential energy change? Well, no, because, for example, x1 minus x2, right? We would then have to put it instead x1 prime minus x2 prime, but that's just equal to x1 plus a sub x minus x2 minus a sub x. And as you could see, our a sub x's cancel out, and this is just equal to x1 minus x2. So the distance between our 2 points doesn't change, right? The distance between our 2 points doesn't change. And so this whole second part of the Lagrangian doesn't change either. So L is equal to L prime as we suspected. All right. That was it took a long time, but I hope no one has any confusions about this part. All right, for the rest of this video, we are now only going to consider the one-dimensional case instead of the three-dimensional case like I was just talking about. Just because the one-dimensional case has everything we want to do, but doesn't take as long to write out. So we have two particles, particle 1, which is at position x sub 1, and particle 2, which is at position x sub 2. Our Lagrangian is now equal to 1/2 times m1 x1 dot squared plus 1/2 m2 x2 dot squared minus v, which depends only on x1 minus x2. All right? All right. So what we want to show is that the total momentum of these two particles combined, which is m1 times x1 dot plus m2 times x2 dot, is conserved along paths which obey the equations of motion. So let's say that x1 bar of t and x2 bar of t are our paths which satisfy the equations of motion of our system. And the bar is just notation. That means it's the true path. So in order to show that momentum is conserved, we're going to do a trick. And I don't even know if it's really even fair to call it a trick, because it's really the fundamental trick to understanding Noether's theorem. And it's going to take a little bit of time to fully explain the trick. But let's start by saying, let's start on explaining the trick. So we're going to consider a tiny variation of both of these paths. So x1 bar of t is now going to become x1 bar of t plus epsilon of t, and x2 bar of t is now going to be x2 bar of t plus epsilon of t. And epsilon of t is some, function of t, that we're thinking of as a little tiny function. Just a little tiny variation. So you might be thinking, oh, well, this is just like the Euler-Lagrange, this is just like the proof of the Euler-Lagrange equation. But it's not exactly like that, because in the Euler-Lagrange equation, we had two epsilons, epsilon sub 1 and epsilon sub 2. We were considering all little variations of these two paths. Here, we're not considering all little variations, we're only considering a specific little variation. namely the one where epsilon sub 1 of t is equal to epsilon sub 2 of t, right? So in the Euler-Lagrange equation, we have no such equality. But here, our trick is that we're going to consider this specific variation. And what is this variation exactly? Well, it's sort of like varying x1 and x2 together as a little translation. So in other words, we're adding a little time-dependent translation that's wiggling x1 bar and x2 bar, back and forth. Like, you might consider it to look like t. You might consider it to look just like some little translation that's like wiggling back and forth in time. All right, now I want to define my action, S. And I want S to depend on what path x of t I'm considering. And by x of t, I'm using x of t to sort of refer to x1 of t and x2 of t. So x1 of t is the coordinate of our first particle, and x2 of t is the coordinate of our second particle. And I'm sort of lumping it together into just x of t. So let me just move this to the side. Yeah. Okay. So S of x of t, right, equals the integral between 2 times t1 and t2 of L of x of t and x dot of t. Now, and dt. Now, what I want to consider is S of x bar of t plus epsilon of t, right? We're now, by that I just mean this path right here, right? The one where I'm adding epsilon of t to both coordinates. So, as we've discussed in the Euler-Lagrange equation video, this can be written as just the action of the x bar of t path. So S of x bar of t plus delta S, where delta S is to the first order in our tiny variation epsilon, plus, I'm kind of running out of space, plus order epsilon squared terms. So order epsilon squared terms. And in order for, so if x bar of t is stationary, which is exactly what it has to be to satisfy our equations of motion, then delta S equals 0. So delta S has to equal 0 for any tiny variation from our true path x bar. That includes this tiny variation that we have here, which is a tiny time-dependent translation. So this condition right here is what we are now going to expand out in order to see that our momentum is conserved. All right. So now let's just write that same exact thing again. So S of x bar of t plus epsilon of t equals S of just x bar of t plus delta S plus epsilon squared in higher terms. So I'm going to stop writing like the of t's here. So I'm just going to write x bar and epsilon and not like write the parentheses t, just because it gets kind of tiring. Okay. Let's now write out exactly what this action is. So it's equal to the integral from t1 to t2 of 1/2 m1 times x1 bar dot, remember this is a function of t, plus epsilon dot, remember epsilon is also a function of t, I'm just not writing of t anymore, squared, plus 1/2 m2 x2 bar dot plus epsilon dot squared minus v of x1 bar plus epsilon minus x2 bar minus epsilon. And then all of that times dt. All right, so first thing to notice is that these two epsilons right here cancel out because we have plus epsilon and minus epsilon. Now the next thing we want to do is to expand out the kinetic energy terms. So the integrals from t1 to t2 of 1/2 m1, and now we have x1 bar dot squared, and then we have plus 2 x1 bar dot times epsilon dot plus epsilon dot squared plus 1/2 m2 x2 bar dot squared plus 2 x2 bar dot times epsilon dot plus epsilon dot squared, and then once again minus v of x1 bar minus x2 bar, and then all of that times dt. Now, these epsilon dot squared terms are in our order of epsilon squared terms. So, whoops, that wasn't, I don't know why that happened. There we go. So we don't have to keep them to the next line. So I'm going to rearrange the previous line to be the integral from t1 to t2 of 1/2 m1 times x1 bar dot squared plus 1/2 m2 times x2 bar dot squared minus v of x1 bar minus x2 bar. Oops. So, whoa. All right, I see why it's happening. So, that was just this term, and this term, right? I just wrote them out front first. All of that dt, and then I'm running out of space, I'm going to go to the next line, plus the integral from t1 to t2 of m1 times x1 bar dot times epsilon dot plus m2 x2 bar dot times epsilon dot, all of that times dt. So those were just these terms, this term, and this term. And now I'm also going to add on plus O of epsilon squared. And that was just this term and this term, which you don't really care about. So we can see that this right here is equal to this. And clearly, this is equal to this. So, therefore, this thing right here is equal to delta S. All right, now here comes everybody's favorite part of the video, the part where I clear everything away. An extremely satisfying part of the video. Okay, so put this up here. All right, so we want to say that 0 equals delta S, which is equal to this thing. And I should say that this is only true if we have the boundary conditions that epsilon of t1 equals epsilon of t2 equals 0, right? That's really the condition that we need in order for delta S to be equal to 0. If you just think about the proof of the Euler-Lagrange equation, our true path only has delta S equal to 0 if we have these boundary conditions. Okay, so now that we have our delta S and we know it's 0, we want to change it up a bit how it looks. And we're going to do that by integrating by parts. So if you can't remember how to integrate by parts, well, first of all, you should, but it's really easy with functions like this, because the first term, where we don't have it inside of an integral, we just evaluate, we just sort of cover up these derivatives. And then the second term, it picks up a negative sign, and we sort of transfer a derivative from one term onto the other term. So by the end of this video series, you're probably going to be really good at integrating by parts. All right, so let's integrate by parts here. So the top expression is now equal to m1 times x1 bar dot times epsilon plus m2 times times x2 bar dot times epsilon evaluated at t1 and t2, that was the first term, minus the integral from t1 to t2 of, I'm going to write it outside here, epsilon, took the epsilon outside, times m1 times x1 bar double dot plus, oh no, the phone is ringing, m2, all right, well, it's probably like a scam call, times, oh, yeah, that sounded pretty fake, x2 bar double dot, all times dt. So notice that this first term right here has these two epsilons in it, right? And we're evaluating it at T1 and T2. But those two epsilons are equal to 0 at T1 and T2, and therefore this whole term is just 0 minus 0. Now, for the second term, we can see that this whole integral is equal to 0. And actually, I'm going to just put that right there, just so we can look at it right in the center. All right, 0 equals this integral. Now, notice that this integral is 0 for any epsilon of t. Assuming that, epsilon of t1 equals epsilon of t2 is 0, but it's true for any epsilon of t. Therefore, this thing right here in the brackets has to be equal to 0, because otherwise the whole integral wouldn't be equal to 0. So therefore, we have shown, therefore, 0 equals m1 times x1 bar double dot plus m2 times x2 bar double dot, and this is just equal to d dt of m1 x1 bar dot plus m2 x2 bar dot, which is just equal to the time derivative of our total momentum p. So we have just shown that the total linear momentum of both of our particles is conserved because it doesn't change in time. All right, so you might be thinking now, like, whoa, that's pretty cool. We just proved that momentum is conserved. But you might be kind of wondering now, actually, I'm still a little bit mystified by why this all worked and stuff. And it's going to become clearer as the videos go on, what all the philosophy of this is. But it seems a lot like the proof of the Euler-Lagrange equation, right? And actually, let's clear this and let's make a little comparison. So here, in my first column, I'm going to have proof of the Euler-Lagrange equation. And in my second column, I'm going to have the proof of d dt of our momentum is equal to 0, right? So in the proof of the Euler-Lagrange equation, we considered all little variations epsilon sub I of t, right? Those are all the little variations. But here, we only considered all little space translations, right? Or actually, I should say time-dependent space translations, where in the notation we had previously, epsilon of t was equal to epsilon sub 1 of t was equal to epsilon sub 2 of t. So for the Euler-Lagrange equation, once we did this, actually let me change colors. Once we did this, we got the equations of motion for a stationary path, right? So we set, delta of s equal to 0, and then we got our equations of motion. But here, we got a conservation law, d dt of the momentum was equal to 0 on stationary paths, right? It's on stationary paths, stationary path. So here, delta of s equal to 0 gave us d dt of p equal to 0. So because we only considered a subset of tiny variations, right, and not all the possible tiny variations there were, instead of getting our full equations of motion, we got something a little bit weaker, but also something that is a little bit more insightful, which is that we got our conservation law, right? So that's sort of like how our proof that momentum is conserved is a lot like the Euler-Lagrange equations. We only consider tiny spatial symmetry, tiny time-dependent spatial translation variations instead of considering all the little variations. And instead of getting the equations of motion once we said our path was stationary, we instead got a conservation law. So in the next video, we're going to do the same exact thing, but for rotations. And instead of momentum being conserved, we're going to find that angular momentum is conserved. And you might be thinking like, oh, well, I don't want to watch the same video again. But we're also going to show something else interesting, which is that what if your system isn't symmetric under rotations? Then we're going to find that the angular momentum actually does change in time, and the amount that it changes in time is given exactly by the torque. So that will be pretty interesting, I think.